Hello, welcome to Functional Bar. My name is Charles, and in today's video, we'll be discussing recursive functions. It's a big word, it's a big mathy word. It just means a function that's defined in terms of itself. And to do our study today, we'll be looking at the Fibonacci sequence. Hopefully this is old hat to everyone here. You tend to study this, or at least I did in middle school a little bit, high school, and then again, I think even in college. It's just a well-known, well-loved sequence, and we see it all over the place in industry. Amongst other places, some project management teams or Scrum teams, especially Agile teams, will use a Fibonacci sequence to compute complexity, and it's often an interview question. So today we'll start by looking at the Fibonacci sequence, what it is. Then we'll write the Fibonacci sequence as a function in Haskell, and we'll see that that looks a lot like what it is in math. And then we're going to actually go work through how that function gets evaluated, how we can solve that function, and see that the recursion is not scary, it's not magic, it's just a normal process. So let's go ahead and get started. First thing to note is we have a new comment style. We don't need a whole video for this comment style. I'm just going to quickly show you. Open squiggle dash, dash close squiggle. That's how you make a multi-line comment in Haskell. 2 dashes in front of every line is also, which we've been doing up till now, is also perfectly valid. It's just a little bit easy like this. This is what we normally do, but it's a little bit easier for long comments to have this style for the comment block. So this is a Fibonacci sequence, and like I said before, hopefully this is old hat to everyone. Maybe you just don't quite remember it from 20 years ago, or even yesterday, depending on where you are at in your life. But what we see is that for every value at n, the first value, the second value, we're going to call that n. And so for the first value of the Fibonacci sequence, it's 1. The second value, it's 2. I'm sorry, it's also 1. First and second are both 1. The third value is 2. The fourth value is 3. And we get this by definition. It is defined as 1 is 1, 2 is 1, and everything after that, we just add the previous 2 elements together. So 3 is 2 because we've added 1 and 1 to get 2. And then to get 4, we're going to look at what it is for 3, the 2. We're going to look at the 2 and the 1, and we're going to get 3. And then for 5, we're going to add 3 and 2. So how we write this out in math and in Haskell, it's actually almost identical, except in Haskell we don't have subscripts. I'm going to call it fib, not f. Fib is a simple function. It takes one argument as an integer or an int. We're not using the integer type, we're using the int type. And then it gives us an int as a return. It tells us what it is. So if we give it 2, we want a 1. If we give it 4, we want a 3. Now this is a little bit new syntax. It's called pattern matching in the head of the function. So we just, by definition, we say, hey, fib at 1 is 1. There's no way around that. We don't compute it. It just is. That's how it's defined. Fib at 2 is also equal to 1. And that is also by definition. So you see 1 is here, 2 is here, and that's just by definition. Now some definitions might start at 0. We're starting at 1. And for everything else, we're going to do, it's fib at n minus 1 plus fib at n minus 2. So that means, so we're looking at a 3 here, n minus 1 is going to be this 2, right? And then n minus 2 is going to be this 1. So we're n at 4, it's n at 3. I'm sorry, fib at 4. F at 4 minus 1 is 3. F at 4 minus 2 is 2. So we're going to walk through some more examples of that in a minute. But this is just the mathematical definition. If you look it up, you're going to find something that looks almost exactly like this, except the n and n minus 1 are going to be subscripts, and the f is going to, instead of fib, it'll probably say an f with a giant capital F. And you see down here, I've already filled in the boilerplate code. It's already here, so we don't have to watch me write it. And then we can just stack run it. And fib at 1 is indeed 1, as we would expect. So that looks right so far. Now, how did the compiler get that? So it looked at fib at 1, and it said, I know a function named fib, and I know it takes a single argument, so everything looks right here. Let's go look at that function named fib. Well, fib with an argument of 1 is just 1. We're done. That's all it has to do. Super easy, super quick. And if we change this to a 2, it's going to be the exact same story. We have another 1 as our answer, which is what we would expect because fib at 2 is 1. It does the same thing. It says, I know a function called fib. I know it takes an argument, and this argument is 2. So I'm going to look at my function. I've got some things to pattern match on. Is 2 a 1? No. Is 2 a 2? Yes. Then the answer is 1. So let's look at something a little more interesting. Fib at 3. And remember, we're expecting it to be a 2 as the answer. So we're going to run this real fast, and I'll show you what the compiler does. And so we get 2 as the answer, so it looks right. But let's walk through this function a little more. So the compiler says, oops, fib at 3. I know a function called fib, and it takes an argument 3. An argument. So is fib at 1 3? No. Is 3 a 2? No. Is 3 an n? It can be. We can replace n by 3. So let's try that. So fib at 3 is equal to all of this, except we're going to replace all the n's with a 3. There are only 2, so it's pretty fast. Now, that's not an answer yet. We have more work to do. So we can reduce it though. The compiler knows how to do this. The program it generates knows how to do this. So it moves right along. Fib at 3 minus 1 is really fib at 2. And then fib at 3 minus 2 is fib at, I'm sorry. Yeah, no, that's right. Fib at 3 minus 2 is 1. And guess what? We know these answers already because it's by definition. But the compiler we haven't got there yet. So we look at fib at 2. Do I know fib at 2? Yes, fib at 2 is 1. Do I know fib at 1? Yes, fib at 1 is 1. So that's a 1. And then we just have to complete simplification, and it's 2. And this looks a lot like algebra because it is a lot like algebra. And we see the recursion here isn't anything scary. We just keep calling that function again and again until we have an answer. And those are often called the basis case, this 1 and the 2 here. So if you're going with a well-known mathematical function, you just follow the definition. The mathematicians who produced it already know how this works. They've already done that work for you. And sometimes in industry, you might run into this case where you have a mathematician you're working with and he gives you the formula or she gives you the formula, then you can just write it out. In most cases, you're going to sort of invent a formula on the fly. And so when you do that, you're going to have to oh, okay, well, I just need to make sure there's a basis case. This is a recursive function. It's defined in terms of itself. What's the basis case? And usually they're pretty obvious, sort of depending on what you're doing. But for right now, what you need to focus on is how we evaluate these. So we have fib at 3. We now got the answer, and it's correct. Oops. Let's try fib at 4. It's a little bit more interesting. I'm going to go ahead and run it first. We expect fib at 4 to be 3. And indeed, we got 3. I'm going to move this up. It should be fine, but my face is over there, so it is 3. As we would expect. So let's get started. So we say, what's fib at 4? Compiler encounters this as fib at 4. Do I know that? No, but I know there's a function. And when I look, it's 4 1. Nope. It's 4 2. Nope. Well, let's go try to figure out this equation. Let's solve this equation. And we do that by replacing all the n's by 4. It's fib at 3 plus fib at 2. Now fib at 3, we don't know the answer to this one yet. but we know how to figure it out. It's the same thing we just did. We put in our same function, we replace all the n's by 3's. I'll get there in a minute. Let me spread this out so we can see our terms a little better. And then we have plus fib at 2, and the compiler sees that. It knows what fib of 2 is by definition. So fib of 2 is 1. So that side's done. That half is done. Let me spread this out more. All this is 3 minus 2 is 1. 3 minus 1 is 2. So we still have more work to do. Fib at 2 is 1 by definition. Fib at 1 is 1 by definition. So the compiler knows that already. It just says fib at 1 is 1. We've told it that. We still have our 1 over here because we can't simplify it. And now we just have some basic addition. So fib at 4 is equal to 1 plus 1 plus 1, or 3. And so now we're done. There's actual extra step if we need to. I am occasionally pedantic, so we'll follow through with it. And so that's all there is to it. Again, there's more work, but it's not more complicated work. There's just more of it. So our equation gets longer, our formula gets longer and longer with each step as we expand that recursion. Excuse me. So let's go ahead and do 5, and then nothing is going to be more difficult than 5, because 5 is going to have us expand both of these all the way with the whole formula. We're not just going to simplify it to a term we already know. So let's run 5, and we see that 5, we expect to get 5, which is nice. It's a nice result. Let's make sure that's what we actually get. Excuse me. And we did indeed actually get 5 as our result. So let's work through this. Just like before, the compiler's like, is 5-1? No. Is 5-2? No. Is 5n? No, but it could be. Let's try making 5n. So we're going to replace all the n's by 5. 5 minus 1 is 4, and then 5 minus 2 is 3. As I fail at math while I'm typing. And then we have, we just keep going, fib at 5, fib at 4. Do we know that? No, but we know how to figure it out. It's the same thing we just did. Let's spread this out. Fib at 3, do we know? We don't know that either. So we're going to do the same thing. We're going to put our formula in and replace all the n's by 3. And then we just keep working through it, just like we have before. Don't know fib at 3, so we're going to have to replace that one. I'm going to have to line up the plus signs again. So you see it? And see how this could get really tedious if we had fib at 500 or something. Fib at 2, however, we do know the answer to. It's by definition. We told the compiler that, so it can just replace fib at 2 with 1. And look, we have fib at 2 again. We can just replace that by 1. We have fib at 1, which is also by definition, the compiler can just look that up. So fib at 1 is 1. So see how fib at 3 evaluated all the way down just like it did before. It's the very first one we did up here. Not quite done. We haven't added the two ones together yet. Oops. Three minus 1 is 2. 1 plus 1, close that out, plus 1 plus 1 is 2. So we can simplify that. We're ready to go. Strictly speaking, we could like if all of you almost certainly know, we could go ahead and lump that one together and make that a 3. I'm going to leave it like this because this is the sort of like the left-hand term, the n minus 1, and then this is the right-hand term, the n minus 2. So I'm just going to leave these separate. We look up fib of 2. Again, the compiler's like, what's fib of 2? Oh, it's 1. You see how this basis case, again, comes right back to how we solve this. We just keep expanding it until we get to the basis case. Fib at 1 is 1. And now we have only numbers, so we can actually answer this question now. So it's 1, 2, 3, 4, 5. Let me write that out just to be pedantic. Oops. So you see we just expand it, keep replacing it by itself, but it's not quite the same, right? Because each time it's going to be n minus 1, so it'll be fib of 4 instead of 5 minus 1, or fib of 3 it works down to, etc. It just gets bigger and bigger. We just expand it, and then we get down to only numbers, and then we can solve it because we only have numbers. And that's very similar to what the Haskell program is going to do at runtime. It does a lot of logical manipulation, which is really cool. It's in contrast to other types of languages, which are going to be working with a very different computational model. So we've got that. Now, that should cover, I'm just going to comment it out so we have working code again. And even though we ran it, I made changes to the file, so I ran it again just to make sure. So now, where do we go from here? This is Fibonacci sequence. We're worried not so much about the Fibonacci sequence as recursively defined functions. And so the recursively defined functions, we have two already, a basis case. And sometimes, usually, that's just one definition. Here, for the Fibonacci sequence, it's 2. We know what the Fibonacci sequence is because it's been defined. Mathematicians have told us. You can read about it on Wikipedia. Just like go use your favorite search engine and type in the Fibonacci sequence. You're going to get a lot of results. A lot of people know this. It's a well-loved sequence. And that's why I used it, because it's used everywhere, and this isn't the first time you've seen it. And we see that the Haskell program is pretty straightforward. It's exactly like the sequence. Now, how do we practice with this? Well, you can look up other sequences, or you could just invent a new sequence. And it doesn't have to be difficult. Right? That's all you have to do. It doesn't even have to be that. That's a recursive function for sure. And we know that n minus 1 is never going to be less than 1. And this isn't quite a total function. We'll worry about that later. Just pass in good values and it'll be okay. And then we could work through that. And you can study that. 30 is quite large, so maybe you want 3 instead. So every item, every element is the first one plus 3, is the one before it plus 3, and then compute out the sequence by hand, and then you can run it a few times and make sure that the program is generating the numbers you want. And that's what I would do to kind of practice this. I would spend a lot of time, and I did, when I was learning recursion, I spent a lot of time with pen and paper. Now I've showed you here in my editor, and if that's what works for you, that's great. You should do that. But for me and for many other people, it works a lot easier if you have a notepad and a pen and you work through a similar exercise as this. You just, even though the program is doing it, it's not doing anything magic. It's the same thing we would do if we were solving it by hand. So you can go through and you can work through it by hand and convince yourself that the recursion is just like we just keep replacing it until we get to what we know, until we have a solution that we can add it back together. One final thing to note, performance. And this may come up if you're talking to your friends who are like, oh, recursion's scary. Recursion's not scary. We just went through it. There's a tiny bit of a learning curve for it. Just practice a little bit. It'll become intuitive really fast. But for other programming languages and other languages that are not Haskell or not functional, you often have to be concerned with something called a stack overflow, which could happen because of recursion if you're not careful. The reason that happens is because for those languages and not for functional languages or languages like Haskell is because of the way they implement function calls. It's very different. And so you're susceptible to stack overflow. Now, there is something now called tail call optimization or sibling call optimization. Most languages now, most compilers for most languages are going to have that. You may have to turn it on, but most of them are going to have that. So if you're worried about recursion in a different language, just turn it on and it's fine. There's a couple of gotchas with how to use it, but it's not that big a deal. You just make sure that the call to the function is the last thing. And here, in fact, it is, or it's very close to it. All right, so let's recap. We learned a new kind of comment, the multi-line comment. It's real easy. The open squiggle followed by a dash, and then we close it with the dash followed by the closed squiggle. You don't have to use it, but you'll occasionally see it. We talked about what the Fibonacci sequence is, just real fast, and then we implemented the Fibonacci sequence and noted that it looks an awful lot like its mathematical definition. We just encoded it a bit differently because we don't have subscripts. Then we went through that with all of its values. We went through sort of what the compiler or the generated program is going to be doing. It's certainly how we would do it by hand on pencil and paper. And we walked through how we get the result on each of these different values. And then we made sure that that value is what was actually computed down here in our main function by just executing it with our show R. This is all just old hat stuff. And then we talked about how to maybe practice this by generating our own sequences, or if we want to look up other sequences in on Wikipedia or something, there's lists of them. And then we wrapped up, and that's it. So as always, questions and comments are welcome. Please click like and subscribe. Thank you for watching, and I hope you have a wonderful day.